So indeed, Ed Bell is here. I am Ed Bell. And I'd like to start by placing a couple of questions to you. And the first question I want to ask is, how is it that an illustrator can create an illustration from something that can't be seen? How does an illustrator take hardly any facts at all, surround them with his or her own imaginings, and create a piece that doesn't cross the border between scientific visualization and fantasy? After 14 years at Scientific American as the art director, I had the privilege to work with a number of first-rate artists, wonderful editors, and some brilliant scientists across many scientific disciplines. And one of the things that stood out to me in dealing with scientific visualizations was that there were two aspects that seemed to happen over and over. One is fairly obvious. A good, successful visualization must be accurate, it must have all the data, and the data must be easily accessible to the viewer. But the second took me a longer time to get, and that is that the visualization must also have a certain beauty, a certain elegance about it. Because it's in that beauty and elegance that there's an engagement with the viewer and with the reader. At Scientific American, I'm used to presenting visualizations that have to disseminate information to a lay audience. So for me, clarity is important, and engagement is important, because a rich engagement usually means a deeper understanding of the information. So how is it that an artist can walk that little delicate line with few facts and a lot of imagination and still be real? Well, one of the analogies I like to use is taken from a book by Michael Crichton, Jurassic Park, in which he has his scientists recreate dinosaurs using the DNA from dinosaurs obtained in the belly of a mosquito. But when they do that, they realize that there are gaps in the DNA from the dinosaurs. There's missing information. But the scientists recreate that information, fill in those gaps using animals that are related, either physically or by lineage, so completing a picture that would necessarily be incomplete otherwise. And so this is how visualizers, especially those in the paleo field and the astronomy field, which is where I am working these days, this is how we sort of complete a picture in which the data is sort of short. Visualizing planets, exoplanets especially, as you'll see later in my talk, is where I spend most of my days after leaving Scientific American. This first piece that I have here for you shows a painting by the father of paleo artist, Charles Knight. It's called Leaping Lizards, and it depicts a T-Rex leaping on top of another T-Rex. So the question is, was this data known to be true at the time that Knight drew this image, painted this image? Really, the fossils that were being obtained around the early 20th century, paleontologists were more concerned with how these animals even stood or walked, much less how they leaped on top of one another. So no, this was not known to be true. But then what justification did Charles Knight feel would honor something like this? And this is where he got the inspiration from. He knew that during his time and during our time, some lizards do jump. And he inferred that if that's the case now, then surely they might have done exactly that then. And while scientists in his time couldn't say this was not so, they really weren't that thrilled that he was that bold in his depiction of this visualization. But Knight's work sort of works on the second level that I mentioned with the visualization. It's beautiful. It engaged the reader. It reinvigorated and popularized paleontology quite a bit in the early 20th century. And his works now are still hanging in museums and walls all over the country. Let's take a look at something else. This is a work by the patron saint of planetary artists, Chesley Bonestell, and it shows a twinkling night sky with Saturn rising above the horizon of one of Saturn's moons, Titan. And here, Bonestell does the same thing that Knight does. He borrows from what he knows to be true, because what was known of Titan at that time was really very little. But he knew that standing on Earth you could see a moon quite clearly, and he reasoned that standing on the moon you would probably see the Earth equally as clear. So he felt justified in this sort of depiction. Sadly, like night, this turned out to be incorrect also, as Titan, we now know, is shrouded in a dense cloud layer, and seeing stars is not possible. Seeing Titan may be on a good night. Here we have an opening image, a visualization for an article on the twilight of the Neanderthals, the last days of this hominid species. We have a lone Neanderthal staring out from a cave looking over the Mediterranean Ocean. And it's quite a beautiful and engaging work. It's done by Kazuhiko Sano, who passed away a few years ago, one of my favorite artists. Sadly, this visualization has an error in it. And even more sadly, one of our readers found that error. The error turned out to be at the end of the Neanderthal spear. Little barbed hooks at the end of the spear. And it was factually known that Neanderthals did not use tools that had barbed edges to them. Homo sapiens did, and maybe another species, but not the Neanderthals. And so this particular visualization has an error in it. And an error in a scientific visualization is like a dagger, it's like a stake in the heart of a vampire. It pretty much kills it. Is that the only error that's in it? Can we trust this piece? So the answer here is no. Again, a visualization must be accurate and it must be beautiful. This one only supplies the second half of that formula. Both Knight and Bonistel use sculpture to begin their works. And I too use sculpture in my work, although my realm, my field, is the virtual space of 3D software. And here you see a scene from Lightwave, which is the software I use. And in this project, which I've done just for this demonstration, I've laid out a flat plane which I ultimately want to turn into a terrain, some sort of landscape. And what I do is I create an overhead view of what that view might look like in grayscale. And here I've superimposed it on top of a screenshot from Lightwave. It's a simple grayscale image in which, once applied to the plane, the software will interpret the darks of the image as being the lowest elevations and the brights in the image to be the highest elevations, and all the grays in between will represent the other variations. And you see on the left side of this screenshot, it's been applied, and I now have a terrain that has a canyon running through it. On the right side, I have that same terrain, but I've painted a texture that I've applied to that terrain, sort of simulate a sort of mossy, grassy look. And now, like Knight and Bonistel, I can place my camera at various positions within my terrain, getting a look at some area that I might want to paint or depict. Here I'm spinning that very same piece of terrain using a fixed light source so I can examine and hopefully find some sort of attractive shading or shadowed area that might work for me. But of course, in a 3D program and with what I mostly do, I can also send a camera through it, thus looking again for spots I might want to illustrate or just to create an animation. Again, what you're looking at here is very rudimentary and very rough and was created in really less than an hour. To take this to a level where it becomes artwork requires much, much more time. Now, what's clear about this image is absolutely nothing. This was supplied by a scientist to Ron Miller and I for a book that I was working on at the time, an iPad app book called Journey to the Exoplanets. And they were very excited about this image, and rightly so. The left side shows an oval, orangey brown oval, that represents a protoplanetary disk, an early evolution of a solar system. And the detail to the right contained a detail from that disk showing little red blobs and little blue blobs. And those red and blue blobs were meant to be worlds, were meant to be big chunks of stone and rock and asteroid that were colliding into each other and burning up, filled with hot gases. And believe me, you could almost feel their toes curl as they were describing this to me. And I was like, oh, I think we can do something a little better than that. And this is what Ron Miller came up with, which I think caused their toes to curl even further. A beautiful rendition of an early stage in planetary formation. Here again is a second image that caused the hairs on the back of their neck this time to stand up. And this is, and rightly so, because this is the first exoplanet that was photographed using an optical telescope, the Hubble telescope. And basically 2 images were taken of the same area 2 years apart. And you can see that in the lower right-hand side in the detail, which says 2004, the pixel was there, and in 2005, oh my God, it moved that far, which in astronomical terms is eureka, break out the champagne time, because that little dot turns out to be a planet. Not only a planet, but a ringed planet with rings apparently that were even larger than that of our own ring planet, Saturn. So we couldn't wait to visualize this for them, and this is what Ron Miller came up with. A really gorgeous image. The rings here, again, we use a technique here that both Bonestell and Knight use. That is to say, we infer from Saturn's ring structure that it might look like this. We do not know that the ring structure looks exactly like this. And by that same reasoning, we've incorporated about a half a dozen moons within that ring structure, knowing that it's very likely to be. And the scientists confirmed that, yes, we don't know that they're there, but more than likely they really are there. What I like to do with visualizations is to take the viewer, place the viewer in a place that's unexpected, a place that they've never seen an image from before. This is a standard view of Jupiter with its giant red spot in the lower half of it. And the red spot in and of it by itself is an amazing environmental condition. It's a 400-year-old cyclone, hurricane, if you will, that's been spinning on that planet, again, for 4 centuries. But one of the unique things about it that's seldom talked about is that it's actually raised a little bit from the surface of the planet. So I asked Ron to drop us down right next to the red spot, and let's see what it looks like from there. And this is what Ron came up with, a wonderful picture, image, visualization that appeared in Scientific American in an article called 8 Wonders of the Solar System. Here we see the red spot from below, and even from this position, Jupiter's sky is bluish, which is pretty amazing. He also shows little teeny thunderbolts dropping down into the core of Jupiter. Those teeny thunderbolts are each about the size of Manhattan. This, I've taken the viewer up the side of a canyon now in an animation that I did before revealing a giant ice plain on a moon of a ringed planet, of an unnamed exoplanet. And again, this is a way of revealing something in a unique way without just showing the viewer what it is first. Once I've taken them up the side, I can then give them a panoramic view showing an under the ground river pouring out into the canyon. About a year and a half ago, I was commissioned by PBS and NOVA to create a series of animations for a documentary called Chasing Pluto. They wanted me to show what it was like on the surface of Pluto, and this documentary was to air simultaneous to New Horizons' arrival at the planet. And this is basically what we had to work with. This is what Pluto looked like before New Horizons got there. So we were sort of kind of nervous about what we might show. On the other hand, there was a great deal of data that was non-visual that we could interpret with scientist guidance. For instance, we knew that volatiles on the planet, depending on the season, would actually dissipate into the air as sort of gases. And then during other seasons, for instance, when it got colder, those very gases would congeal and drop down back to the surface as snow. So we knew we could show things like that on the surface. And in fact, here's New Horizons as we depicted it, arriving with several asteroids in the area. And we put those there because Pluto is in the Kuiper Belt, and it's known to be very busy there. As a matter of fact, that was one of the things the scientists were worried about, that the spaceship, after its 9-year journey to get there, might be crushed the moment it got there by an asteroid. Here we're depicting snowfall on the planet, on Pluto, with its moon Charon rising in the background. One of the things we had to worry about, and this is something that all visualizers of planets need to take note of, is that we had to be careful the rate at which the snow fell, because we knew for a fact that the gravity on Pluto is much less than it is on the Earth, and so things will fall to the Earth much more quickly. It's this kind of information that Hollywood tends to get wrong when they do the sci-fi movies. As a scientific visualizer of this type of thing, though, you have to be keenly aware of the characteristics of the planet, the moon, the body that you're depicting. Does it have an atmosphere? What is the atmosphere made of? How big is it? How strong is the gravity? Is a moon circling around it close or near? Is it close to its star or near to or far away from its star? All of these things will affect how you visualize it. Currently, I'm working on an animation, again for PBS, dealing with Titan. And Titan has an atmosphere. And because it has an atmosphere, it can convey sound. So any sounds that I play during that animation, I have to make sure are correct, because they're not going to sound like they do on this planet, because it's not oxygen that the vibrations are rippling through. It's hydrogen. It's methane. Here we see those very same volatile, that very same snow that was falling in the previous scene, escaping back up into the atmosphere later on in a different season on Pluto. Pluto has 4 seasons. Each season runs about 40 years long. It takes 200 and odd years for Pluto to get around the sun. This was something we were really happy about. We guessed that there might be canyons and mountains on Pluto, and sure enough, when New Horizons flew by, it captured imagery that showed that there were. So this turned out to be sort of prescient on our parts, and we were very pleased to be able to show that. Here again was something that we got right. Large areas of iceless and snowless plains, near plains that actually had contained large bodies of ice. Here's something I got wrong. Wanted to show liquid neon on Pluto. A few scientists suggested that might actually be found because it's so cold that neon would actually be liquid. As it turned out, the documentary didn't air this scene, and I was actually glad that they didn't, because in addition to New Horizons not finding any liquid neon, the rippling that I did in the animation on the surface of the liquid neon, I decided later on was overly done, because it's not enough atmosphere to cause water to ripple that greatly. A year and a half later, we did these recent animations on Pluto to show what it actually really does look like. Once this asteroid goes by, you'll see Charon and Pluto as they actually do appear in a starry sky. We also took a sort of fantasy look at a research vessel skimming over the surface of Charon, since we now know have a pretty good idea what it looks like. Skimming over the surface of Charon on its destination to a planet we now know a lot more about. Hope everybody enjoyed my presentation. Thank you.